great privilege and pleasure for all of us at CSIR-National Geophysical Research Institute, which is celebrating its Diamond Jubilee, and large geoscience community in India to welcome Professor Michael Brown, a very distinguished geologist from University of Maryland. We missed Professor Brown. He was expected to come during the International Geological Congress, but we are so delighted and pleased that in a very short invitation, he has kindly agreed to deliver the third CSIR-NGRI Diamond Jubilee lecture. Today is a very important day for America and of course for CSIR-NGRI when we are going to receive and listen Professor Michael Brown on this very fateful day of CSIR-NGRI. He is going to speak on very contemporary topic, especially which is very dear to the scientists of CSIR-NGRI, knowing the fact that a large group of the researchers have traveled across major parts of our country which are having metamorphic rocks. We work on metamorphism, and in the present day, when everybody is talking to trace when plate tectonic started, the role of metamorphism becomes very important. We know that in Earth, the crustal metamorphism is predominantly associated with the convergent plate boundary and subduction to collision orogenes. And metamorphism is classified in of different types, and knowing about the type of metamorphism, the pressure and temperature path, and its variation over space and time is very important in the understanding of, particularly when we are trying to trace the pre-Cambrian geological history. And on today, we are going to listen on such a very important topic, and Professor Brown, who is known globally for his work on this important geological issue. I am also very pleased to welcome many distinguished geologists of our country, the former directors of our institute, Professor Gupta, Professor Dimri, our members of the Research Council, and the distinguished scientists, geologists like I can see Professor D.M. Banerjee and many others. So with this small welcome, I once again put on record our sincere thanks to Professor Michael Brown for agreeing to our request to deliver the third Diamond Jubilee lecture. And about Diamond Jubilee celebration, I request the chairman of the celebration committee, Dr. Poonchand Rao, to briefly talk about the plan, how CSIR-NGRI, while contributing large geoscience discoveries as well as the interventions for the societal benefit over 6 decades, is not only celebrating its achievements but also introspecting and learning from the studies done globally to make a future plan for the decades. With this, I thank all of you for joining this event and welcome you on this very fine evening and morning of United States. Thank you very much.
Thank you very much, Dr. Tiwari, and once again, a very hearty welcome to all of you to this very important program today. This is the third Diamond Jubilee lecture that NGRI is having. We have had extremely eminent speakers coming on this podium and sharing with us their vast experience in their respective fields. And of course, today we are extremely delighted and privileged that we have Professor Michael Brown. And before I invite him to deliver the lecture, I'd like to say a few words about this glorious milestone that NGRI has achieved. As you all know, that the National Geophysical Research Institute has been a premier research institute of the country and has made tremendous contributions in the last 60 years of its existence, thanks to a large number of leaders who have committed, who have dedicated everything to the growth and success of this institute. And in fact, we are very fortunate today. We have at least two of our former directors, Professor Harsh Gupta and Dr. V.P. Dimri. Hearty welcome to both of you, sir. And of course, we have a galaxy of very eminent people, including our RAC members, and I think RAC chairman also is joining us. So it's a very glorious moment for the institute to be celebrating the 60th year of its existence with all the wonderful contributions. And of course, this will continue, the celebrations will continue up till October 2021. And each month we are inviting a very eminent speaker. Now coming to the speaker of the day, and it's my very proud privilege to introduce Professor Michael Brown. Of course, he's a very well-known scientist, a very well-known personality worldwide, but nevertheless, it's my pleasant duty to introduce, for the sake of a large number of young people. I think they're all joining to listen to this wonderful talk that's coming up. Professor Michael Brown, who is currently at Maryland University in the United States of America, is an internationally recognized figure in the field of metamorphic geology, particularly crustal melting, petrogenesis of granulites and eclogites, metamorphism and tectonics. Professor Brown had his PhD from the University of Keele, UK in 1975, and he has over 45 years of experience in the field of metamorphic geology. Before moving to the University of Maryland in 1990, he was a professor in Oxford Brookes University at Kingston in UK, Kingston University. He has about 29 book chapters and 138 articles in peer-reviewed journals to his credit. And his articles are widely recognized among the geoscience community, as is evident from his amazing citations of about 13,500 and an impressive H index of about 67. He has been bestowed with several awards and recognitions from the Geological Society of America, the American Geophysical Union, Mineralogical Society of America, Mineralogical Society of Great Britain and Ireland, Geological Society of London, and so on. In fact, he is listed in the A to Z of Earth scientists of the world, which includes about 150 notable Earth scientists since the 18th century, and I think that's a great credit. That's a great thing to his credit. In fact, I'm very glad to tell that in Hyderabad there was a conference called Granulites and Granulites in 2013, in which there was a special session called Brown Session, which was dedicated to understanding the 40 years of contribution of Professor Brown. I think it's a very special credit to Professor Brown, I would say. This is he was also the president of Mineralogical Society of America till 2019, and closely associated with the society in various capacities. He is the founding editor of the Journal of Metamorphic Geology, which is a very high impact factor journal, as you all know, and he has served in the editorial boards of several esteemed journals like Geology, Journal of Geological Society, Geological Society of London, and so on. He is also serving as the associate director at the Center for Global Tectonics, China University of Geosciences, Wuhan, and is a member of International Precambrian Research Center in China. He has supervised many doctoral and postdoctoral students across the globe. And of course, he has conducted several short courses, workshops, etc. in the field of metamorphic petrology. So with these few words, I'd like to invite Professor Michael Brown to deliver the very interesting talk today. And of course, a few questions we'd be happy to take in the end. Over to you, Michael.
I think Michael is, his mic is muted.
I just unmuted myself. Can you hear me now?
Yes.
Yes.
Good evening. Thank you very much for the invitation. It is a privilege to have this opportunity to take part in the Diamond Jubilee lecture series. Congratulations to NGRI. In my talk today, I want to address secular variation, and I want to try and link metamorphism, tectonics, and global glaciations, because I believe they might be related. What I show on the first slide is the present-day surface heat flow of the Earth, and it's clear that Earth loses heat through the ocean basins, and that heat loss occurs through the mid-ocean ridges. So the tectonic mode of Earth is a direct reflection of the necessity for Earth to lose heat. So plate tectonics is the mechanism by which Earth loses heat at the present day. Now, the theory of plate tectonics, as I'm sure you all know, was built on data from the ocean basins. The problem with this, when we try and take plate tectonics back in time, is that the age of the ocean lithosphere is less than 200 million years. The oldest lithosphere, the oldest significant area of oceanic lithosphere is Jurassic in age. So this poses the question of how may we take tectonics back through time if the primary evidence for the development of the theory of plate tectonics came from the ocean basins. And of course, we're fortunate in having continents which provide an archive of Earth's history. But unfortunately, that archive is not complete. We must expect survivorship bias. We know that as we go further back in time, we have a smaller proportion of the rock record preserved, particularly prior to the Proterozoic. And you can see in the map on the right, the distribution of Archean cratons shown in pale blue, and they take up only a small percent of the continents, and the continents themselves, of course, only form 1/3 of the surface area of the globe. Another way of looking at the problem is to look at the position of Earth in the solar system and to look at the tectonic mode on the 5 active large silicate bodies. These are shown here, and we don't need to worry too much about most of the information on this slide. The critical information is at the bottom. And what this tells us is that plate tectonics is an unusual tectonic mode in the solar system. It is not the norm. The norm in the solar system is that the tectonic style is a single or stagnant lid of one kind or another, perhaps heat pipe, vigorous, sluggish, but it is not plate tectonics. Plate tectonics is an unusual tectonic mode, and we should bear that in mind when trying to determine how far back we can take plate tectonics on Earth. From this information, we can erect a null hypothesis. The null hypothesis would be that Earth has always operated in a plate tectonics mode. I will use PT as an abbreviation for plate tectonics for convenience. The alternative hypothesis that we would erect as a complementary to that would be that further back in time, plate tectonics evolved from a different tectonic mode, such as stagnant lid or sluggish lid. And this would be consistent with the evidence that we see in the solar system as a whole. Now, of course, in science, we test the null hypothesis. So in this talk, we will test the hypothesis that Earth has always operated in a plate tectonic mode. We can ask the question, why might this null hypothesis be false? And the answer to that is that we believe Earth's mantle was hotter in the past. This is an inevitable consequence of back calculating radioactive decay. So if the Earth's mantle was hotter in the past, it's plausible that plate tectonics may not have been possible and that Earth may have operated in a different tectonic mode, as indeed we see on other silicate bodies in the solar system. So what I show here is simply a calculation on the left using the global heat balance equation and a simple parameterization for heat loss, showing that Earth may have had a peak temperature around the Mesoarchean, Neoarchean, and that the temperature of the Earth's mantle has declined since down to the present day. And on the right, I show some data from petrology, estimates from petrology of mantle temperature. Gang and Fen shown as boundary lines between their range of estimates. The estimates from Condi 2016 shown in the gold yellow color, and the petrological estimates from Herzberg et al. Based on their estimates from what they believe to be primary melt compositions from the mantle through time. Regardless of the amount of secular cooling, I think it's clear that Earth's mantle was warmer in the past, and this is something we have to bear in mind. So this leads us to the question, if continents are the archive of Earth's history, what can we learn about the record of crustal metamorphism? So the aim in dealing with secular change in metamorphism is to quantify the temporal variation in the thermal condition of the orogenic crust using the metamorphic rock record, and to relate this to secular change in mantle potential temperature and tectonic mode. So to do this, we need information from the metamorphic record. The information we need is primarily what I call the thermobaric ratio, the ratio of the peak temperature to the peak pressure. So of course, the things that we calculate are temperature and pressure, which we calculate the thermobaric ratio. But we also need to know the age when that mineral assemblage from which we calculate the peak pressure temperature conditions was equilibrated. And the rate determining step in terms of the number of localities for which we have good information is the age information. We have many more determinations of pressure and temperature than we do have reliable determinations of age. So what I show here is the location of the 564 locations for which I believe we have robust pressure, temperature, age information. These range in age from Cenozoic to Eoarchean, although it is true that the data are sparse before the Neoarchean. And this data set, which is available online, was finalized at the end of February 2018. So here I show the PT conditions derived from those 564 locations. And these data represent a point, commonly referred to as the metamorphic peak, on a geotherm crossed during a dynamic orogenic evolution, either from lower to higher thermal gradient, or higher to lower thermal gradient. So in a petrological sense, either in a clockwise direction or a counterclockwise direction. The other thing I want to emphasize is that by careful selection of the data that we use in this data set, we hope to minimize the errors associated with the necessary assumption of synchroneity among TP and age for some localities where the age was not directly linked to the PT conditions. As many of you know, the field of petrochronology has developed in the last decade, and this is the field that where we try to link a particular age to a particular PT condition. So we can replot these data according to the characteristic rock types. And we can look at the data in relation to metamorphic fasces. We can look at the data in terms of their thermobaric ratios. And we can look at the data in terms of thermobaric ratio versus age. So the relationship between these data and metamorphic fasces is shown in the top left figure. The relationship between these data and thermobaric ratio is shown in the top right. And the relationship between thermobaric ratio and age is shown at the bottom. And the data are color-coded so that the data in blue, which we might refer to as high pressure or ultra high pressure metamorphism, but I also refer to as low thermobaric ratio metamorphism. There are 189 examples. They all have a thermobaric ratio less than 375 degrees C per GPa. And they're typified by blue schists and low temperature quartz eclogites or ultra high pressure coesite bearing eclogites. The data shown in the yellow-orange color represent what I originally called eclogite high pressure granulite metamorphism, but which I now refer to as intermediate TP metamorphism. There are just over 150 of these shown plotted. They have a range of thermobaric ratios between 375 and 775 degrees C per GPa. And they're represented by high pressure upper amphibolite and granulite fascist rocks and medium to high temperature eclogites. So this is the field where we have the overlap as a consequence of bulk composition between plagioclase bearing high pressure granulites and plagioclase absent medium to high temperature eclogites. And then shown in the dark red is the field of granulite ultra-high temperature metamorphism or high TP metamorphism, 220 samples, all thermobaric ratios greater than 775 degrees C per GPa, characterized by upper amphibolite and granulite fascist rocks, including ultra-high temperature granulites. I will come back to the relationship between thermobaric ratio and age. So let me deal with that now. What I want to discuss here is the development of bimodality. You're probably all familiar with the work of Miyashiro, published in Journal of Petrology in 1961, that identified paired metamorphic belts. What I show in the additional diagram now on the left is a plot of the data from the last 200 million years, shown as pressure versus temperature in the top, and as the log of thermobaric ratio versus frequency at the bottom. And this demonstrates clearly that in the last 200 million years, the period for which we know for certain that we had plate tectonics, because that's when we have a record of oceanic lithosphere, and we can understand the kinematics of plate tectonics for the last 200 million years. We had a bimodal distribution of metamorphism between lower temperature pressure metamorphism and higher temperature pressure metamorphism, shown in both figures. We can also see, if we look at the plot of thermobaric ratio versus age, that this bimodality developed in the Paleoproterozoic. We can see the beginning of it here, and we can see that there are a small number of locations where we have low TP metamorphism in the Paleoproterozoic. This can be better quantified, and we did this in 2019 with a postdoctoral researcher, Holder, and this is shown here. So now the 564 locations are binned by age range, older than 2.2, 2.2 to 1.4, 1.4 to 0.85, and less than 0.85 down to 0.2, and 0.2 to the present date, the data I just showed you. You can see that the development of bimodality is a gradual process. We can quantify that, and it turns out we can model the data that are older than 2.2 giga-annum as a unimodal Gaussian distribution at the 95% confidence level. But as we come into the Paleoproterozoic, we see that the development of a bimodal mixed Gaussian distribution that becomes wider with time. And this can be quantified again with linear regression of the logs of the TP ratios. And this shows that the bimodal distributions of TP become increasingly distinct with time. So bimodality in the metamorphic record is confirmed by this statistical evaluation, and we see that it becomes increasingly divergent with time. Now that poses the question of how we should interpret this. And I first started this work in the early 2000s, and I made a suggestion in a paper in Geology in 2006. And I'll read it as a quote: "A duality of metamorphic belts, reflecting a duality of thermal regimes, appears in the record only since the Neoarchean era. A duality of thermal regimes is the hallmark of modern plate tectonics." This is the concept of paired metamorphic belts introduced by Miyashiro. "And the duality of metamorphic belts is the characteristic imprint of plate tectonics in the rock record. So the occurrence of both high and intermediate TP metamorphism since the Neoarchean marks the onset of a Proterozoic plate tectonics regime, which evolved during a Neoproterozoic transition to the modern plate tectonics regime, characterized by colder subduction as chronicled by low TP metamorphism." Now, when I published this, a professor of geophysics at ETH Zurich wrote to me, Taraskeria, whom I'd known since he was a PhD student in Russia, and he said, "We can test this hypothesis, Mike." And he suggested that we get a PhD student to do some thermomechanical modeling. And this is part of Elena Sizova's PhD thesis. And what we can see here are the results of one particular model from one of the studies that she did. And in the sequence of 3 diagrams on the right, it shows the mechanism of exhumation for UHP metamorphic rocks at present-day conditions at the top, and with increasingly warmer mantle temperatures in the second and third figures down the sequence on the right. And what you can see is that we have exhumation by translithospheric diapirism when the mantle temperature is set at the present day value. But as we increase the mantle temperature, we have a wide extensional area, and we have no ability to produce ultra-high pressure metamorphic rocks, or at least to produce and exhume and preserve in the rock record ultra-high pressure metamorphic rocks. And the reason for this, we thought at that time, was that there was the difference in the strength of the subducting slab, and the subducted slab at the present day breaks off at about 300 kilometers or so depth after collision and after subduction of continental lithosphere to mantle depths. That continental lithosphere can then be exhumed and preserved in the rock record. However, when we increase the mantle temperature, we get increased slab rollback, and we get a much shallower breakoff of the slab, which means that we no longer bring any continental lithosphere back to crustal conditions, and we have a wide, high temperature, low pressure belt behind the original site of collision. That kind of explanation, in a slightly different way, was confirmed recently by Chowdhury et al. In EPSL last year. Their model is slightly different in that they argue that the mantle component of the lithosphere peels back, so it still rolls back, it peels back, it preserves the continental crust in a thickened origin, but the lithospheric mantle continues to subduct. But because it rolls back as it peels back, it generates this wide extensional belt of thinned lithosphere with high TP metamorphism and associated magmatism, whereas we have the intermediate TP metamorphic rocks representing the orogenic welt. So if we take the relatively young part of the metamorphic record, I think we can be fairly confident as to the location of the tectonic setting of the different kinds of metamorphism. So each metamorphic type is associated with a specific tectonic setting. In the case of low TP metamorphism, this forms in subduction channels and at accretionary margins during subduction of passive continental margins. And I infer that this marks sutures in older origins. Intermediate TP metamorphism, involving higher pressures and also higher thermobaric ratios, is associated with mountain building, which generates both the ability to increase the temperature through the enhanced radioactive decay and also the thickening to increase the pressure. I also interpret it to record crustal thickening in older origins, and this is consistent with the modeling I showed you in the previous two slides. High TP metamorphism occurs in orogenic hinterlands, back arcs and plateaus. I think it records the lithospheric extension that we see in older origins generated by this either rollback followed by shallow slab breakoff or peelback tectonics, again involving rollback and thinning of the lithosphere behind the origin in the hinterland. So let me summarize that as three key changes in the metamorphic record. The first of these is during the Neoproterozoic, when we see the widespread appearance of low TP metamorphism. And I interpret this to be the beginning of what I called in 2006, the modern plate tectonics regime. We also see a number of localities in the Paleoproterozoic of low TP metamorphism. And I think this may record localized regions where the style of orogenesis, deep subduction and exhumation of continental crust, was similar to modern plate tectonics. I think this is a plate tectonic regime. It is somewhat different in terms of its thermal structure, and I called this the Proterozoic plate tectonic regime. Now, of course, the metamorphic record becomes quite prominent at the beginning of the Neoarchean, so the question arises, what does this represent? I think the widespread appearance of intermediate and high TP metamorphism records a transition to plate tectonics, that the Neoarchean is a period where we find contradictory evidence in terms of volcanic rocks, whether they record subduction or whether they don't record subduction, and that this is a period of global transition, so that by the early Paleoproterozoic, we are indeed in something we can recognize as a plate tectonic mode. So the increase in data that we see in going through the Archean, particularly through the Neoarchean, may mark an expansion of subduction-driven collision across the globe, and the development of regional linked networks of narrow boundaries between rigid plates. And those networks, of course, have to become global by the Paleoproterozoic, because plate tectonics is a global regime. The gap in data in the early Paleoproterozoic corresponds to a tectonomagmatic lull in the Siderean between 2.3 and 2.2 gigaannum. This has been argued in a number of papers, most recently by Spencer et al. In Nature Geoscience, and suggests the beginning of cyclicity in tectonics, reflected by the uneven distribution of data. The development of bimodality in the data reflects the dual thermal environments diagnostic of subduction-driven collisional orogenesis. And we can perhaps relate this change in metamorphism to the change in metamorphic, to the change in mantle thermal potential temperature. The range of metamorphic TP clearly becomes wider with time. We can see this in this plot here. These are all the data in Holder et al., the 564, simply plotted as a single data set. The range of thermobaric ratios becomes wider with time. And since somewhere around the beginning of the Neoproterozoic, clearly there appears to be a cooling in those data. And that reflects, I think, the mantle cooling, which may have started somewhat earlier in the Paleoproterozoic. It is interesting that the peak here occurs somewhere in the Mesoproterozoic, and that is something I will address in a few slides. So there is always this question about how we should interpret the Neoarchean. And I think this is an important question. Multiple studies identify a change in composition of the crust, the continental crust, from more mafic to more felsic, although there's wide disagreement on when this transition in composition may have taken place between the Paleoarchean and the end of the Neoarchean, between 3.5 and 2.5 GA. So we can ask the question whether the metamorphic age and magmatic zircon age records, I show this at the bottom here, this is the well-known distribution of magmatic zircon ages through time, and the data set is now enormously large, so it's a robust set of data. Whether these identify the first appearance of continental arcs and the production of more granitic rock compositions with their ability to crystallize zircon that becomes quite dominant in the record from the Neoarchean onwards, whereas zircon is much sparser in the record before that time. The record, of course, is also suffers from survivorship bias. And maybe this also represents the first continent collisions, because we know we have to have formed some larger supercratons by the early Paleoproterozoic, because it is the breakup of those supercratons and their rearrangement into Lunar Columbia that identifies the start of what many people refer to as the supercontinent cycle. So it's clear that we can see cyclicity in the metamorphic record, and that cyclicity parallels the record that we see in uranium-lead zircon ages of magmatic crustal rocks. So this begs the question of how to interpret these distributions. How many tectonic cycles can we identify here? 1, 2, 3, 4, 5. And how might these cycles be explained? Do they correspond to the supercontinent cycle? I am going to be slightly heretical here, and I'm about to argue against the supercontinent cycle as it's generally explained. In this slide, I simply show a summary from a review paper by David Evans of various cratonic arrangements that might have been in place in the Neoarchean through to the early Paleoproterozoic. That's to say, before the tectonomagmatic lull in the Siderian. And we can see that we have various clans of cratons that appear to have been part of individual supercraton units prior to their breakup and their reconfiguration in the different components of the supercontinent Nuna, or perhaps Columbia. Excuse me. After the tectonomagmatic lull, the general consensus would be that we have a supercontinent cycle, and that supercontinent cycle extends from the formation of Lunar Columbia in the Paleoproterozoic, shown in a configuration here from Lee's paper in Precambrian Research in 2019. And as we go through the time sequence, in the transition to Rodinia, we open a number of internal oceans that then close. The lunar core is not really disrupted, it remains intact throughout this period. And the Rodinia supercontinent does not represent a major reorganization of the kind we see in the Paleoproterozoic, from the breakup of the supercratons to the formation of Lunar Columbia, or that we see after Rodinia in the Neoproterozoic, the breakup and the rearrangement into the supercontinent Pangaea. So the supercontinent Pangaea represents a rearrangement and loss of the external Rodinia superocean. The formation of Lunar Columbia represents a breakup and loss of whatever ocean material was there at the beginning of the Paleoproterozoic, but the transition from Lunar Columbia to Rodinia represents nothing as dramatic. We can see that reflected in the metamorphic record. What I've plotted here is the moving mean of pressure, of intermediate temperature pressure metamorphism, plotted against the best fit to the data, the moving mean of temperature of high temperature pressure metamorphism, the moving mean of thermobaric ratio of high TP metamorphism, and the PDF of the ages. And what we can see here is that the highest thermobaric ratios occur in the Mesoproterozoic. This is offset by some hundreds of millions of years from what we think might be the highest mantle potential temperatures, which were probably in the Neoarchean. Why might this be? Well, I'm going to argue that there are three geodynamic cycles here. One that leads up to the tectonomagmatic lull between 2.3 and 2.2 GA. One that extends through the time of what many people have called the boring billion to the Neoproterozoic, and one since the Neoproterozoic. So the first of these cycles represents the transition from whatever tectonic mode Earth had prior to plate tectonics to plate tectonics. And yes, I'm making the assumption that the null hypothesis is going to be falsified, or that I have falsified it. I'll address that towards the end of the talk. The formation of several supercratons, and that cycle extends to the tectonomagmatic lull. The second tectonic cycle that we see begins with the breakup of these supercratons after the tectonomagmatic lull, so in the mid-Paleoproterozoic, and their rearrangement during the formation of Lunar Columbia at about 1.9, 1.8 GA, and then internal adjustments, opening of internal oceans and closure as we transition from Lunar Columbia to Rodinia. So this is the well-known period of relative tectonic and environmental stability, sometimes called the boring billion. And as I'm going to show in the next few slides, it has a unique metamorphic and magmatic record, and I'm going to argue that that is due to a plate slowdown. The plate tectonics was active in the Paleoproterozoic. It slowed down through the late Paleoproterozoic, through the Mesoproterozoic to the early Neoproterozoic, and then it became faster again in the mid-Neoproterozoic. The third cycle began with the widespread appearance of low TP metamorphism, and this represents the modern PT regime that I proposed in 2006. But if you're familiar with the literature of Bob Stern, he proposed in 2005, this was actually the beginning of plate tectonics. So we can take the metamorphic data set and we can treat it as a single data set. We don't have to look at it in terms of different rock types or different thermobaric ratios. Maybe that isn't a good way to look at it. Maybe we should just treat it as a single data set of 564 data and see what happens if we analyze it as a single set. And we've done this here. It was published in Geology last year. This shows the data plotted in thermobaric ratio versus age and the yellow symbols. And what we've done here is calculate, we've used sequential analysis by cumulative sum to show how TP changes through time. And we identify a number of significant steps in the time series where the change in the mean is statistically significant at the 95% level. The means are shown by the horizontal thick gray bars. The changes are shown by either the green or the magenta lines, which represent either drops or step-ups. And this analysis clearly confirms that we have a regime in the Archean that extends broadly to the tectonomagmatic lull and the formation of Columbia. We have a regime in the middle part of the Proterozoic that extends to the mid-Neoproterozoic with the highest thermobaric ratios and apparent tectonic stability. This is what I call dominantly supercontinental. This is the Columbia-Rodinia to Rodinia breakup period, where we do not have a dramatic reorganization of the continental lithosphere. And then we have a significant drop in thermobaric ratios through the Phanerozoic. So the metamorphism is anomalous because the highest TP ratios occur in the Mesoproterozoic. Why might that be? The magmatism is also anomalous because if we look at the distribution of anorthosites through time, particularly massive type anorthosites, which are the most volumetrically abundant type on Earth, they are predominantly Proterozoic in age. And if we plot area against age, and if you allow me the option of using area as a proxy for volume, then I think we can argue that the biggest volume of anorthosite magmatism occurred in the Mesoproterozoic. So we have anomalous metamorphism in the Mesoproterozoic, anomalous thermobaric ratios, the highest crustal metamorphic conditions in the Mesoproterozoic, and we have the dominant, volumetrically dominant anorthosite magmatism. This needs an explanation, and the explanation I'm going to offer is that this was due to a plate slowdown. I ask you to treat the next few slides carefully because this material is currently in review. It has not yet been published. So what would be the consequences of a plate slowdown? Well, we don't really have direct constraints on Precambrian plate velocities, but we can perhaps use the distribution of passive margins through time as a proxy. In the Mesoproterozoic, passive margins are very few in number, shown in the top graph, but they're very long-lived, up to 600 million years at 1500 MA. This suggests that there might have been a plate tectonic slowdown. We can test this hypothesis using mantle evolution models, and this is what we've done in the paper in review. Using the lifetime of passive margins as a proxy for average plate age, we estimate average plate velocities through time, assuming similar plate size. And this is shown in the graph at the bottom, where average plate velocities at the present day, maximum plate velocities at the average plate velocity at the present day, average plate velocities decrease to the Mesoproterozoic, and then perhaps increase back through the Archean. From the plate velocities, we can calculate mantle temperature back to the Paleoproterozoic, assuming standard mobile live convective scaling and integrating T back from the present day. That's shown in the top graph, and the circles are the estimates of Mantle TP from Herzberg et al. Based on what are thought to be primary melt compositions. You can see that they correspond well. Using the variation in mantle temperature, that would have implications for the volume of melting. Higher mantle temperature produces a higher degree of mantle melting. A higher degree of mantle melting produces melts with higher magnesium number. Melts with higher magnesium number have higher densities. Higher density melts are more likely to stall at the MOHO or in the lower crust. Now, we don't actually have a good proxy for mantle melt compositions through the Proterozoic, but we can perhaps use Gavreau's as a proxy for melt. I realize that some of these are going to be cumulate, maybe all of them are going to be cumulate, so this is not an ideal proxy, but it's the best we have. So at the bottom right, I show the distribution of magnesium oxide on the left versus age as a KDE, and the distribution of density on the right, calculated from the variation in mantle temperature shown at the top. And what you can see is that as we go back in time, we have melts with higher magnesium contents and higher densities. Based on that information, we can calculate the distribution of melt emplacement by depth. Now, melt gets emplaced all the way through the crust, and some of it, of course, arrives at the surfaces and extruded as volcanics. And what we show here from right to left is the calculated distribution of melt versus crustal density for the Phanerozoic, then the average Proterozoic crust, and then the average Archean crust. So the average crustal compositions are based on the crust 1 seismic model. And what we can see is that a much higher proportion of melt is placed around the depth of the moho for the Proterozoic crust than for either the Phanerozoic crust or for the Archean crust. We can plot that as the ratio of extruded melt versus total melt, and that is shown in the graph in the upper half of the diagram on the right. The curve in blue shows the relationship for an evolving crustal composition from Archean through to the present day. The curve in red shows the information for a constant crustal composition taken as the Proterozoic crustal composition. In both cases, it demonstrates that we have a low in the extrusive to total melt ratio in the Mesoproterozoic. We have a higher proportion of extruded melt at the present day and through the Neoproterozoic and the Phanerozoic. The magenta boxes show independent estimates of extrusive to intrusive magmatism from 2 locations in Australia, and of course the estimates made from 2 studies at the present day or in the recent past. So a plate tectonic slowdown after the formation of Nuna Columbia and before the breakup of Rodinia, again, this is the period some have called the Boring Billion, provides conditions that were just right to generate the maximum TP of metamorphism and the peak of anorthosite production. But that raises another question. What caused the plate tectonic slowdown? And that requires that we ask, what controls, if you like, the rate of plate tectonics? And this comes down to the role of friction. And this next information, pair of slides, comes from the work of Sobolev and Brown, published in Nature in 2019. What we show on the top left is a plot of plate velocities for one particular model of present-day plate velocities versus calculated velocities from a particular model with coefficient of friction at convergent margins of 0.03 and coefficient of friction in transform and divergent margins of 0.1. And this shows a very good match with actual measured velocities. This demonstrates that we need weakening of convergent margins to model current plate velocities. And the value used in this model, 0.03, is shown here. This is the variation in friction coefficient as we increase the amount of sediments in the trench. Without sediments, the friction coefficient is going to be high. With sediments in the trench, the friction coefficient is low. So it appears that there's a role for sediments in the trench in controlling the rate of plate tectonics. And this has been modeled previously by Sobolev along the Andean margin. We all know that there's an increase in sediment as we go from north to south down the Andean margin, and there's a change in style of the orogenic belt, the plate velocities, and the degree of extensional rollback as we go from north to south along the Andes. That's clearly related to the amount of sediment fill in the trench. So this led to a hypothesis that we challenged the view that secular cooling of the mantle was the only major control on the emergence and evolution of plate tectonics since the Mesoarchean. Remember, this was the hypothesis from my 2006 paper and the modeling by Sizova et al. And Chowdhury et al. That there was a relationship between secular cooling and the dynamics of subduction. So based on the main controls on variations in plate velocity and the stability of subduction, we proposed that the emergence and evolution of plate tectonics on Earth was related to the rise of the continents above sea level, sometime probably during the Neoarchean, possibly slightly earlier in places, and the accumulation of sediments at continental edges and subsequently in trenches to lubricate and stabilize subduction. We did test this with a variety of data that I don't have time to show, but that is in the published Nature article from 2019. And we focused in particular on two major surface erosion events following the Paleoproterozoic Huronian glaciation and the Neoproterozoic snowball earth glaciations. We argued that these events provided an increased sediment to supply to continental edges to lubricate subduction, and that this played a crucial role in reactivating plate tectonics after a period of reduced subduction, first after the tectonomagmatic lull between 2.3 and 2.2 GA, and second after the boring billion in the Neoproterozoic. So this is shown here in the plot I showed you previously. So grounded ice sheets reached sea level at all latitudes during both of these glaciations. These were the two largest surface erosion events in Earth's history, each producing a large volume of sediments in trenches to lubricate subduction. So we might annotate this with the Neoarchean was a period of stabilization of subduction, the development of a plate boundary network, and the emergence of plate tectonics. We had increased tectonic activity after the tectonomagmatic lull, driven by the sedimentary fill in the trenches that lubricated subduction, allowing faster plate tectonics and the development of the lunar Columbia supercontinent. A period of decreased tectonic activity, higher mantle heat flow under continental lithosphere, giving higher TP ratios, more stability, allowing basaltic magma to fractionate and create anorthosites during the dominantly supercontinental period of the boring billion. And then after the snowball earth, vast amount of sediment in trenches, increased tectonic activity, significant subduction of continental lithosphere to mantle depths, and cooling of subduction zones reflected in the metamorphic data. We can ask a final question: does glacial erosion control deep continental subduction and therefore ultra-high pressure metamorphism? Before the cryogenian, high pressure metamorphism is relatively rare, and ultra-high pressure metamorphism is almost absent. This shows the data for low TP metamorphism. There are a few locations in the Paleoproterozoic, but most of the data, as you know, occurs from the late Tonian down to the present day. Why might that be? Cases of HP and UHP metamorphism coincide with glaciations, the Huronian glaciation here, the snowball earth here, and multiple glaciations during the Phanerozoic. This correlation suggests to us that deep subduction of the continental crust was enabled by a combination of sediment lubrication of the plate interface, and as a consequence of erosion to generate those sediments, an increase in slab pull due to plate thinning. A number of cases of HP-UHP metamorphism occur in the mid-Paleoproterozoic after the Siderian low-latitude glaciation, but most of them, as I said before, since the cryogenian. If we plot the younger data on an expanded axis, and also plot more information about the glaciations, we see that the periods of low latitude glaciation during the Phanerozoic are always followed by peaks in ultra high pressure metamorphism. This suggests that there is a relationship, which is unanticipated, a connection between the climate of Earth's surface and the extreme depths to which continental crust can be subducted. In the middle of last year, the National Academy of Sciences in the United States published a plan for the National Science Foundation Earth Sciences for the 2020 to 2030 decade. It was called Earth in Time, and they identified 12 priority questions that NSF should investigate in the coming decade. One of these was identified in the introduction. When, why, and how did plate tectonics start? Clearly, that's the one we're interested in here. I actually don't think that's the right question. Why not? The first thing we have to do is ask, what is the critical condition for plate tectonics? What do we have to demonstrate if we want to argue for plate tectonics? And the answer is that the plate tectonics is defined by the creation and maintenance of a network of narrow plate boundaries separating a fragmented lithosphere. If we want to argue that plate tectonics was the mode operating in the Archean, we need to be able to demonstrate that we had a global network of narrow plate boundaries separating a fragmented lithosphere. I don't believe we have the rock record to do that. What we do identify commonly is subduction. So that poses the question, does subduction equal plate tectonics? Well, we have subduction on Venus, but most people don't think there is plate tectonics on Venus. It follows then that subduction does not identify plate tectonics. To argue that plate tectonics operated before the Jurassic, which, if you remember, is the age of the oldest oceanic lithosphere, requires more than evidence of subduction. It requires evidence of a global network of narrow boundaries and multiple plates. But the evidence is limited by survivorship bias, as I mentioned at the beginning of the talk. Hence, it may not be possible to determine if early Earth had plate tectonics. We simply may not be able to accumulate enough evidence that whatever we see was global rather than regional. The geological record may only allow a lower limit on the emergence of plate tectonics, and we published a review in the annual reviews of Earth and Planetary Sciences last year, in which we argued that we can take plate tectonics back to the early Paleoproterozoic because we can demonstrate mobility of the cratons during their rearrangement from the breakup of the supercratons to the formation of Lunar Columbia. But it is much more difficult to demonstrate a global regime of narrow plate boundaries and mobility and plates prior to the tectonic magmatic lull. A better question might be what tectonic modes were possible before plate tectonics. How might each mode have transitioned to plate tectonics? And are there observations and inferences from the rock record to exclude any of these options? Now, in terms of thermal modeling, there are generally considered to be 4 possible tectonic modes. An active lid mode, which includes plate tectonics. And plate tectonics describes the surface kinematics of plates. It's an active lid mode because the lithosphere participates in the mantle convection via the formation of weak zones that define narrow plate boundaries, allowing the lithosphere to sink back into the mantle. Sluggish lid also involves subduction, drip-like or blob-like or short slab or unstable subduction, but it occurs on a locally confined scale associated with lithospheric mobility. This could easily be what we see when we see evidence of subduction in some volcanic sequences in greenstone belts in the Archean. An episodic mode is self-explanatory, transient between a stagnant lid and an active lid mode, and stagnant lid is self-explanatory. The important thing about this is that 3 of these different modes involve subduction, potentially. If subduction can be associated with more than an active lid mode, then identifying evidence of subduction, if it is reliable, still isn't evidence of plate tectonics. So we can again ask a final question. This is the last slide. Do plate tectonics and subduction have the same birthday? So plate tectonics, as I've said, is a kinematic theory that describes the behavior of a fragmented lithosphere. It can be demonstrated to have operated back to the beginning of the cryogenian. I think everybody agrees on that, including Bob Stern. And this is the modern plate tectonics regime that I suggested in 2006. Subduction had become a dominant process by the end of the Neoarchean, so it is likely that the Proterozoic was dominated by a mobile lid tectonic regime, and this is what I called the Proterozoic plate tectonics regime in 2006. You can see these beginning of these 2 regimes, or the outline of these 2 regimes shown here. Prior to a Neoarchean transition to plate tectonics, Subduction may have started multiple times, but may not have been stable on a hotter Earth. Thus, initiation of unstable subduction and periods of regional mobile tectonics do not equate with stable subduction and plate tectonics. Regional evidence of subduction does not confirm global plate tectonics. Subduction and plate tectonics have different birthdays. Thank you very much for your attention, and once again, it's an honor to have been asked to present this talk.
Thank you very much. Thank you very much, Professor Brown. That was a very interesting and yet very lucid talk. You have taken us through a wonderful journey where you explained the duality of metamorphism and of thermal regimes, and which is the hallmark of plate tectonics. You were very convincing when you showed the connection between the thermal regimes and the stages of plate tectonics, and then also the initial signatures of the first continent-continent collision. You have also connected 3 geodynamic cycles in the last 3 giga-years, and you shared some of the latest results on the time series analysis of TP in the last 3.5 billion years. And it was, of course, a very interesting term to hear from you, the boring billion. I think that's something we could ponder over. You also showed us the role of friction in controlling plate tectonics, the connection between orogenesis, the trench filling, and the rate of convergence. That was very interesting. And later you moved on to the role of glaciation in secular variations of metamorphism, how the glacial erosion connects with deep continental subduction and UHP metamorphism. Finally, you connected the tectonic modes with several theoretical possibilities, and you ended with a very nice question: do plate tectonics and subduction have the same birthday? So in all, I think it makes an extremely interesting talk, and it was so simple and lucid for all of us. I really appreciate, and thank you very much for this wonderful talk. But I would, if you agree, I could invite a few questions from the audience.
Please go ahead.
Yeah. So do we have some questions from the...
Sir, there is a question by Dr. Srinivas.
Okay. Dr. Srinivas is here, or you could read out the question?
Yeah, his question is, what would be the reason for increased erosion rates following snowball earth conditions? What would be the reason for increased erosion rates following snowball earth conditions?
Was the question about erosion rates following snowball earth conditions?
Yes.
Erosion rates, based on recent papers, are very high when we have low latitude glaciations. So it is an expectation that low latitude glaciations will lead to high erosion rates and large amounts of sediments in ocean basins.
May I ask a question here? Mike?
Yes?
Yes. You talked about the boring billion. The boring billion, the term boring billion was introduced by Martin Bezier, not for slowdown of a plate tectonics, but for isotopic variation changes, lack of isotopic changes to study the economy. So how do you relate these two?
I'm sorry, I didn't say anything there.
Boring billion was started by, or rather suggested by Martin Bezier from Oxford. And that he considered boring billion because there was no isotopic shifts through the entire Mesoproterozoic.
Yes, that's correct. That's correct. It's interpreted as a period of environmental stability. Environmental stability reflects tectonic stability. That tectonic stability reflects a slowdown in plate tectonics and a limited amount of orogenesis, a limited amount of subduction along certain continental edges at a decreased rate compared with the rates that produce the amalgamation of the cratons into New Columbia, and the breakup of Virginia, and their reconfiguration through the Phanerozoic into Pangaea. And that stability is a consequence of the lack of sedimentation going into trenches, increasing the friction, decreasing the rate at which plate tectonic behavior takes place.
The whole concept of boring billion is now being challenged by the whole concept of boring billion is being challenged nowadays because it's no longer considered to be boring because there are so many changes which can be now identified and documented.
I think you were saying it's not boring, is that correct? And I agree with you. I agree with you. It's a name that people are familiar with, and it's more familiar than we refer to, which is the Proterozoic glacial gap.
Okay, I think Dr. Tiwari has a question. Dr. V.M. Tiwari.
Yes. Is it clear? Maybe good
yes,
that yes. Others can mute their mic. Professor Brown, it's really wonderful listening the entire history of the Earth formation through different processes, and one of them you very nicely talked about the plate tectonics. I wonder that do we have convincing evidences of change in plate motions during the Phanerozoic coinciding with like ice age or little ice age, so that the kind of the hypothesis we trying to test during the Archean or Proterozoic can be validated.
I'm sorry, I missed something there. You were asking about testing a hypothesis in the Archean Proterozoic, but I missed what you were proposing.
Yeah, but I am just trying to understand that during Phanerozoic, the present day plate tectonic processes operative, there have been changes in the plate velocities.
Oh yes.
And do the change coincide with the glaciation events, like we had the ice age or the other temperature changes in the atmosphere?
Yeah, I believe from the modeling we did that we can see gross changes in plate velocity back through time, so that we have a low in the Mesoproterozoic and higher rates in the Phanerozoic and potentially in the Archean. We need to be a little careful. The modeling that we did is probably reliable back to the Paleoproterozoic. I don't think it could be regarded as reliable back to the Archean. It is extraordinarily difficult to estimate plate velocities in the past. And of course, we would like to be able to estimate them on a timescale similar to the Phanerozoic, where we know that there were changes in plate velocity related to changes in plate configuration, for example, that can occur on short timescales. We simply do not have the ability at the moment to model this kind of behavior earlier in Earth history. And the use of the passive margins, which are many fewer in the Mesoproterozoic, but much longer in terms of their longevity, suggests that we would expect a much slower rate of tectonics. So I think that is a reasonable argument. I therefore think the modeling is reasonable. I don't think it can be taken back before the Paleoproterozoic. And it is, of course, a coarse model. It can't reproduce the level of detail that we're able to obtain from the last 200 million years based on the kinematics that we can get from the ocean basins.
Thank you.
Michael, there's a question from Dr. Bhaumik. I'm just reading it out. He's asking, what is the possible cause of high TP ratios in Mesoproterozoic metamorphic rocks? Is it only due to radiogenic heat production, or there are also mantle heat inputs?
No, I think it's due to the fact that we have a period of supercontinentality which insulates the underlying mantle. And therefore, it's a consequence of radiogenic heat plus higher heat flow from the mantle. Of course, that situation is geodynamically unstable, and that may be why we see the development of these internal ocean basins during the Mesoproterozoic that then close to form the slightly different but very similar configuration of Rodinia. So I think it's mantle heat as a supplement to radiogenic heat that drives the high TP ratios in the Mesoproterozoic. And that's a direct consequence of slowing down plate tectonics combined with a period of supercontinentality.
Okay, thank you. There's also a question from Dr. Srinivas that how long the increased erosion rates might have continued after deglaciation?
Well, after deglaciation, the erosion rates won't continue in the same way. The debris will be transported to trenches and then distributed and subducted. So it's the direct consequence of the glaciation. But of course, there's a time lag between increasing the rates of subduction and generating UHP metamorphism in the Phanerozoic. So we do see that the UHP metamorphism follows on from the period of glaciation. This is what we would expect. The sediment will become available as the glaciers retreat. The plate tectonic rates will increase. We will have better lubricated subduction zones with lower friction, and we will have the ability to subduct continental lithosphere when it arrives at the trench, which takes some time. I mean, we need a collision. When the continental lithosphere, the passive margin, arrives at the trench, it will then be able to be subducted to greater depth and exhumed, preserving ultra-high pressure metamorphic rocks that we do not see widely prior to the late Tonian through the Phanerozoic.
All right, yeah, thank you very much. There's a question from Dr. Prantik Mandal. He wants to know whether crustal accreditation in Neoarchean was dominated by the modern plate tectonics.
In the Neoarchean?
Yeah.
The information we have from well-studied volcanic sequences in cratons like the Pilbara craton in northwest Australia or the Yilgarn craton in southwest Australia, and I'm sure in cratons within India, although I'm less familiar with the literature, the information we have from volcanic sequences is that sometimes they record subduction signatures, and sometimes they do not, and they're interlayered through the Neoarchean. I think this demonstrates that there are periods of subduction, which is unstable, and periods when we don't have subduction, and therefore this is unlikely to be a plate tectonic regime, although it may well be a sluggish lid or an episodic regime that does involve subduction, does involve some mobility, could involve collision, but almost certainly wouldn't be global.
Right, yeah. Maybe somebody from the panel here, Dr. Chetty, you have some question?
No questions, thank you.
Yeah, I know you have been a long associate of Professor Brown. I thought you might be interested to ask something. But yeah, that's fine. Anyone else? We have Professor Singhvi, Professor Harsh Gupta, and several of our senior colleagues. Any questions? Yes, sir. Professor Harsh Gupta.
First of all, I'd like to compliment for a wonderful talk, which covered a very wide topic so very beautifully. And I've just a hypothetical question that all these inputs, how do they fit in with the program of USGS, the Deep Time Digital Earth? Because that is a very ambitious program. And I know that the kind of work that Professor Brown has done would try to be of very high help to this program. Any comments on that from Professor Brown?
No, I don't think so. I don't really have a comment on that. Sorry.
Anyone else? There's one more question from Dr. Mandal. He's asking when the transition between vertical tectonics and horizontal tectonics took place. Any thoughts
They're
on
not terms I use. I don't refer to either horizontal tectonics or vertical tectonics because neither of them is a very good description of either kind of tectonics. We can clearly have a global tectonic regime in which we have diapirism, so-called vertical tectonics, and horizontal movement of plates. So distinguishing the different tectonic modes as horizontal or vertical, in my view, is not sensible. I think we need to think in terms of whether we can demonstrate a global network of narrow boundaries separating multiple plates, or whether we can't. And if we can't, whether we're dealing with the remnants of a global plate network that we can't demonstrate, or whether we're dealing with a regional network that maybe wasn't global and might have involved unstable subduction and periods of mobility and periods with less mobility. I think we need to be much more thoughtful about how we use terms like vertical and horizontal.
Yeah, sure. Yeah. So I think that was a very lively discussion. A lot of questions have come up that clearly shows the response that the people have really appreciated this wonderful talk. If there are no more questions, then maybe I will request Dr. V.M. Tiwari, Director of this very proud institute, National Geophysical Research Institute, to say a few words, and we can perhaps close the meeting.
We may request Professor Sigui, our member of our research council, senior member of Professor, are you still there?
But I will only say I compliment you for a wonderful lecture, very exhaustive work spanning 2 decades. I don't work in this area, so but I could understand the scope of the work that you've been doing, and I'm extremely grateful. I hope we can meet in person and then interact with you with more detail. Thank you so much.
Thank you very much for the opportunity. It's an honor, and I'm very appreciative.
Thank you. The reason why I have requested Professor Singhi that he is also chairing the Ministry of Earth Science Geoscience Committee, and we have been discussing on this issue of how plate tectonics started, a kind of a project which we can work in India. So this is certainly one of the most favorite topic which we can think of listening, and such a importantly describing with data, with lucid presentation. We really had very rare opportunity to listen, and for giving such a wonderful opportunity, we have no words to thank Professor Brown, and as most of our colleagues agree, that we would certainly like to have a personal interaction, and the possibility in future exists. We will look forward to meet and discuss more on this important topic, because there is another thing which really connects the paleoproterozoic or proterozoic accretion of the crust is metallogeny, and how those data can supplement the hypotheses which we are talking of, the subduction and the initiation of the plate tectonics. So the accretion of the crust still remains one of the fundamental important issue in the geosciences, and illuminating on that had been really very nicely done by Professor Brown, and I thank, and we look forward for listening some more talks like this. and our committee members, Diamond Jubilee committee members, have been looking forward to most of the people who can really educate on some of the contemporary science issues. And one of the things which Professor Brown has talked of the 2030, it's a really beautiful document. I have read it and also joined in one of the webinars. So your contribution is wonderful, and we really enjoyed listening today's talk. Thank you very much.
Thank you again. Good evening.
Thank you, Michael. I hope we'll be in touch.